In this video, we will draw the free body diagrams of a frame and analyze the free body diagrams to calculate the support and internal pin forces. Before we begin, I would recommend that you go to the Actus Potentia website and then select Engineering Statics from the pull-down menu, scroll down to free body diagram, and then go to the playlist for free body diagram and watch the videos 2, 3, and 4, because in these 3 videos we discuss most of the fundamentals for drawing of free body diagrams. We click Start and open the free body diagram application. We take 2 straight members, join them with a fixed joint which is equivalent to welding, and build an L-shaped member. Take another straight member, take a pulley, join the 2 straight members with a pin, join the pulley with the straight member with a pin, stretch the cable, join the cable with the member with a pin, stretch this cable, apply a load at the end of the cable by turning the force into a vertical force and choosing its magnitude to be 1000. Apply a pin joint at B and apply another pin joint at E. So this frame consists of an L-shaped member which is welded at A, and a straight member and a pulley. Let's draw the free body diagram. These are the 2 forces coming from the pin at B. These are the 2 forces coming from the pin at E. This is the L-shaped member, and this is the force coming from the pin support. And if you look at the whole free body diagram, this is the pin support, and this member is directly attached to the pin support. So all of this force from the pin support, which is coming from the wall or the floor, gets transferred to this L-shaped member. So if you look at the magnitude of these forces, negative 2438 and positive 2159, and if you look at these 2 magnitudes, you will see that these are identical because the entire pin force gets transferred to this member. This member also has a horizontal force coming from the cable which is attached at this point, and 2 forces, 1Cx and 1Cy, at the pin where the L-shaped member is joined with the horizontal member. In the horizontal member, these 2 forces are 2Cx and 2Cy. In the L-shaped member, the forces are 1Cx and 1Cy. 1Cx, 1Cy, and 2Cx, 2Cy obey Newton's third law, because at this pin only 2 members are joined. So if we look at the free body diagram of pin C, you will see that 2CX and 1CX, that equal and opposite. Similarly, 2CY and 1CY are equal and opposite. This is the pulley. This is where the pulley is attached to the horizontal member. The forces on the pulley are 3dx and 3dy. This is where the pulley is attached, and these two forces are 2dx and 2dy. If you look at the pin D, then you will see 2dx and 3dx are equal and opposite, following Newton's third law, and 2dy and 3dy are also equal and opposite, following Newton's third law. At this point, the interaction between the pulley and the horizontal member follow Newton's third law, because at this pin only 2 members are connected, the pulley and the horizontal member, and so the forces obey Newton's third law. Let's count the total number of forces that you need to determine. These are the wall forces, 1, 2, 2 more wall forces, 3, 4. These wall forces gets transferred to the L-shaped member, and these wall forces get transferred to the horizontal member. So if you look at the L-shaped member, you do not have to count these forces because they are getting transferred from the wall onto the member through the pin, so we do not double count. So our count of internal forces remains at 4. Then we have 5, 6, 7. We do not double count these two forces because they are action-reaction. This is the action, this is the reaction. So 5 plus 2, 6, 7, 8, 9. You do not double count these two because these two forces are action-reaction of these two forces. So altogether we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 support and pin forces. We can write 3 equilibrium equations for the L-shaped member, 3 equilibrium equations for the horizontal member, 3 equilibrium equations for the pulley. That gives us 9 equations, and by using these 9 equations we can determine the 9 forces. This concludes this video.